Hello and welcome from my side. My name is Philipp Kunz from the Institute of Construction Materials at the Technical University of Dresden, and in the upcoming minutes I would like to present our experimental investigations with regards to the diffusion of chlorides in strain-hardening cement-based composites. Therefore, I have set up the following agendas. So we will go firstly into the background why we're using SHCC for our investigation program, to go then a little more in detail into the experimental program we conducted, to present later the results, and then to just summarize what we have learned within the framework of our project. To investigate the durability of a material, such as SHCC in our case, especially with regards to repair applications, together with reinforced concrete, not only the deterioration of SHCC as such, but also the corrosion protection of steel reinforcement has to be considered to assess the durability. In ordinary reinforced concrete, crack width regulation proofs are commonly used in the existing standard and codes for the serviceability design. Since SHCC develops usually lower crack width as ordinary concrete and develops multiple cracking pattern after initial crack occurs, like it's presented on the right hand side in the stress-strain diagram of SHCC, it could be considered a promising material with respect to the durability and is highly suitable for crack related investigations of transport mechanisms. Therefore, we conducted a series of experiments to enlarge the database for the durability related to the properties of SHCC. Within the framework of this paper, the description of the transport mechanisms only focuses on the diffusion itself as a transport process. Therefore, all chloride ingress related investigations were conducted in fully water saturated conditions. This approach was chosen in order to utilize the model approach presented on the right side of this slide, which was published by Altmann et al. In 2012 and describes the chloride-induced SHCC deterioration. Especially the red marked part, which models the crack-related diffusion coefficient, was not yet calibrated. Therefore, the experimental data obtained during this investigation were used to calibrate the model for chloride ingress into cracks. Coming now to the experimental program. The experiments were in principle based on the mechanical preloading to generate multiple crack patterns. For this purpose, dumbbell-shaped specimens, as shown below on the left side, with a length of 500 mm and an investigation length of 200 mm, while having a cross-section in that area of 60 × 100 mm, were produced and subjected to monotonic uniaxial tensile loading. That happens usually after 28 days in order to achieve the typical SHCC cracking pattern. Subsequently, the specimens were cut and coated and subjected to different concentrated sodium chloride solutions with varied exposure times, which we will see more in detail in the coming slides. The mixture itself contains, besides cement, superplasticizer, stabilizer and water, a relatively high fly ash content, fine aggregates with a maximum aggregate size of 0.2 mm, and has in total a fiber content of 2% by volume, where those fibers were made out of polyvinyl alcohol with a length of 12 mm and a diameter of 40 micrometers. The uniaxial tension loading was then conducted at the age of 28 to 30 days. The loading was performed under deformation controlled low cycle tension regime with a loading speed of 0.01 mm per second and 0.25 mm increase in deformation per cycle, which corresponds to a strain increase of approximately 0.1% per cycle, as shown on the left hand side and the bottom of this slide. The deformation was measured by two inductive displacement transducers fixed to the opposite sides of the specimen with a distance of 250 mm as mentioned before. The final state of strain was determined by a 1% residual strain after unloading. After the tension loading, the specimens were then cut according to the cutting regime presented below on the right side. This resulted in two new specimens for the crack evaluation and the chloride ingress testing with dimensions of 50 × 60 × 250 mm. Subsequently, the crack pattern of each specimen was recorded by using a high-resolution scanner with 3600 dots per inch. This resolution enables pictures with a pixel size of around 7 micrometers. On this basis, cracks could be theoretically observed starting by a crack width of 14 micrometers. The crack widths and crack distances were evaluated using image editing software and counted specifically along one central axis. As shown below, the crack width and crack distance were then recorded per specimen in a chart along the length of the specimen. After all crack patterns of each specimen were recorded, the specimens were stored in water tanks to achieve full water saturation. Those water saturated and cracked specimen, as well as the uncracked specimen, were then coated and sealed on 5 sides with aluminum butyl tape so that only the bottom surface remained unsealed. The sealed specimens were then stored in 2 separate containers with different concentrated sodium chloride solutions. One solution was prepared according to NT build 443 with a sodium chloride concentration of 16.5%. The second solution was produced with a concentration of 3%, corresponding to conventional chloride tests. Both sodium chloride solutions were stored at 20 degrees Celsius and fully sealed to minimize evaporation effects. These tests were executed for the cracked and uncracked specimen with exposure times from 3 to 7 days. For the purpose of this paper, only specimens from the 3% sodium chloride solution will further be presented. After removing the samples from the sodium chloride exposure, all specimens were cut to 4 slices of around 10 mm thickness, as presented below on the left. Those slices were then used to conduct the silver nitrate test, where we used a 0.1 molar silver nitrate solution. Silver nitrate reacts on a freshly fractured surface with unbound chlorides to silver chloride, which can be seen on the surface due to its silver gray color of the reaction product. The penetration depth of this silver gray reaction product was then measured and recorded for each crack along the length of the specimen, as presented on the right in the bottom. Furthermore, in case of a higher penetration depth due to closely adjacent cracks compared to an uncracked area and the uncracked horizon, the additional penetration depth, as you can see below, was measured as well and related to the crack distance between 2 cracks. By applying this procedure for each usable surface of each of the slices, we always get 6 values for the penetration depth, meaning in the results of this work, always the average of 6 values are related to a certain crack width or a certain crack distance. Since the silver nitrate test only provides qualitative statements for chloride ingress, we now know how deep free chlorides penetrated the SHCC, but we don't know the chloride content. Therefore, the quantitative analysis of chloride concentration was performed following the recommendations as described in NT build 443 by abrading thin layers of 1 to 2 mm of each uncracked specimen, as shown here on the right side of this slide. Those specimens were exposed to the same exposure conditions as the cracked specimen as mentioned before. 6 to 10 layers of each specimen were abraded to define the particular chloride concentration of each of those layers. This powder test material was then given in 18% diluted nitric acid and filtrated. The specific chloride concentration per layer was then obtained by using a photometer to the filtrate. In addition to the quantitative chloride investigation, the silver nitrate test was conducted as well on freshly cut uncracked specimen in order to investigate the penetration depth of the silver gray reaction product to the uncracked areas. By applying those 2 procedures, we will be able to relate the silver nitrate reaction product to a specific chloride content. Coming now to the results. Crack width distributions were evaluated combining all specimens investigated and grouped by their width, while for each group a range of 10 micrometers was set. The graph below on the left shows the empirical density function for those crack widths. As you can see in this graph, the main amount of cracks occurred to be within 20 and 120 micrometers. The probability density function shows a similarity to a log normal distribution. but a precise statistical description of this function was not investigated for this paper. More challenging was the evaluation of the crack distances, since it is mainly relevant in situations of mutual crack influence between two adjacent cracks. For this reason, the evaluation of crack distance was conducted after the chloride tests. The measurements were performed for all specimens, but only the distance which appeared to have an accelerated chloride transport were taken into consideration. This is presented below in the right chart. Crack influence took mainly place up to 10 millimeters. Relating now together the crack width development along the specimen length and the increase of the qualitative chloride investigation, which is reacting due to the findings of the quantitative analysis at a 0.3 mass percent per binder, we could easily see here that we have a certain function which we can derive out of the experiments, which shows actually that we have an increasing chloride penetration due to a higher concentration and due to a longer exposure with increasing crack width. And combining that with the crack spacing, you can see here a quite close function on the crack spacing and the influencing of the crack each other, where we have the 3 days and 3% natrium chloride solution, whereas we have for the 7 days already a higher variation in the values, but as well we can see an increase of the chloride increase into our specimen due to adjacent crack and the crack proximity. Coming now to a short summary of our tests. So first, chloride diffusion tests were performed on uncracked and cracked specimens, which shows that the main crack width occurred to be between 50 and 60 micrometers, while more than 95% are below 100 micrometers. The smallest crack distance, which we could observe, was below 200 micrometers. And due to the multiple cracking pattern, we could see that most of the crack influencing took place between 2 and 3 millimeters. Based on the qualitative chloride profiles we observed with the silver nitrate tests, it could be assured that beside diffusion, no noticeable other transport process took place. And it was found that the dimension which chosen for our experiments were very suitable for chloride exposure up to 14 days. Qualitative tests itself yielded to no accelerated diffusion in crack-free regions. Thus, it can be assured that crack widths below 25 micrometers do not cause any acceleration of diffusion, which actually underlines the findings of some other authors regarding that item. It should be, however, underlined that the silver nitrate test only considers free and unbound chlorides. The quantitative tests, however, consider both bound and unbound chlorides. This must be taken into account when relating a certain chloride concentration to a moment of the color change by the reaction of the silver nitrate test. Within the framework of this project, specific magnitudes of chloride binding capacity, surface chloride concentration, and diffusion coefficient were calculated. Based on that data, we further calibrate and modify the model mentioned some slides before. With that summary, I would like to close my short presentation, and I'm looking forward for your questions or comments. Thank you for your attention.